Okay, so let's take a look at how we can summarize now and put all of these different terminologies, the names, as well as the energy changes in one diagram. And we're going to talk about what are known as heating curves. And then you will also see cooling curves as well. Cooling curves are just going to be the exact opposites of these heating curves. And what they do is they are going to show how temperature changes as a function of time as we add heat to a system. So let's take a look at an example. And on the y-axis here, we're going to plot temperature. Let's say this is in degrees Celsius, and then we're going to have time, and we're going to refer to this now as the amount of heat added. So if we can imagine an initial situation, let's say we have ice, so solid ice, so ice is a solid, so H2O solid. And then let's say we start with ice at a temperature of, let's say, minus 20 degrees Celsius, right? So that's where we're going to start. And then we're going to add heat. We're going to heat this ice up. And as we start heating it, the temperature of the ice is going to increase. So keep adding more heat, temperature of the ice increases, 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 until we get to a point where the ice starts to melt. And that point at which the ice starts to melt, believe it or not, it's called a melting point. Here. When the ice starts to melt, so here we have, in this region, the temperature of the ice is increasing. We get to the melting point, and then once we get to the melting point, I keep adding more heat, right? You will see that the temperature doesn't actually change, because what's going on here is that the amount of heat that you add goes into now converting the solid ice into the liquid water, right? So the energy goes into allowing those particles to get enough energy to start to now slide past each other rather than being locked. Okay? So we, at this melting point, we have both the solid ice and liquid water present. So we keep adding more heat, temperature doesn't change, it goes into melting the ice into liquid water until we get to a point where all of the ice is melted. And then if I keep adding more heat now, well, then the temperature of the liquid water is going to increase at that point, right? So when all the ice is melted, all we have at that point is just liquid water. I keep heating it, the temperature of the liquid water is going to increase. I keep adding more heat, temperature of the water increases, increases, increases until I get to a point where now the water starts to boil. And at that point, we've reached the boiling point of H2O. And these temperatures, these normal boiling points and normal melting points, these are going to be 100 degrees Celsius with 1.3 degrees Celsius melting point, respectively. So in this region here, I have the temperature of the liquid water is increasing. Okay, and at this point right here, I have the liquid starts to vaporize. That point, and then any additional heat I provide goes into vaporizing more of the liquid into the gas phase. Keep adding more heat, I vaporize more and more and more of the liquid into the gas phase until I vaporize all of the liquid at this point here. Now all I have present is just H2O in the gas phase, and if I provide more energy, well, then the temperature of the vapor starts to increase. So in any heating curve, and again, the cooling curve is just going in the other direction from the top right to the lower left as we take heat away and cooling it down. It's just in reverse. We'll notice a few important characteristics of any such heating or cooling curve. Now, the first thing we'll see is that it's not a strict curve in the true sense of the word. It's actually a stepwise process that's occurring. And there are important regions that we can identify, and these regions here, for example, are the plateaus or the flat regions of the cooling curve, and those flat regions correspond to phase regions. The flat region with the plateaus correspond to changes in phase. And what you will notice again here is that at those points, at those regions, at those phase changes regions, increasing heat doesn't change the temperature. Okay, and that's how we can identify those different phase changes. So the boiling point up in the upper plateau, or the melting point, the lower plateau, right? They're flat because the temperature doesn't change, and the temperature is not going to change the phase change regions. We have the other regions that connect the plateaus, and those represent lines that are sloping upwards. Those would represent the increasing temperature of the respective physical states. So we have the first one here in green. This would be the increase in the temperature of the solid. In region 2, we have increase in temperature of the liquid, and then region 3, increase in temperature of the vapor. Right, so we can visually see what happens if I have a sample of a substance and we increase the amount of heat, what happens to the physical state. We can also correlate that to the changes in temperature as well. All right, so let's take a look at a couple examples involving some calculations using the heating curves, and then also some of the terms we talked about before. So let's take a look at just a couple parts to this question here. Let's calculate the amount of heat deposited on the skin of a person burned by 1 gram of liquid water at 100 degrees Celsius, and then the amount of heat deposited by 1 gram of steam at 100 degrees Celsius. Let's take a look at the first one, A. Right, so what we need here says to calculate the amount of heat. Right, so heat with a Q, we know the heat equation. Q is equal to M times C times delta T. So M here is the mass. C is going to be the specific heat. And then delta T is going to be the change in temperature. So we're given the mass here of the liquid water as 1.00 grams. The specific heat of the water is 4.184 joules per gram degree Celsius. And the change in temperature is always the final temperature minus the initial. So we're ending up at, we're starting off, sorry, at 100 degrees. And then we're ending up at the patient's skin temperature, which is body temperature. We'll assume that's 37 degrees Celsius. So that would be delta T here being equal to negative 63 degrees C. So we have our M, we have our C, and we have our delta T. Remember now, C is sometimes abbreviated as lowercase s in different textbooks, it means the same thing. So you have our heat equals mass 1.00 grams times C 4.14 joules per gram degrees Celsius. And then delta T is negative 63 degrees C. Celsius goes away, grams go away. So we end up with heat now, and our unit left is joules. So that means we did the substitution correctly. That ends up being negative 0.264. And then this would be, let's see here, for the kilojoules, convert it. And the value, the negative, so the sign here, negative value tells you that heat is released. And that's released from the liquid water. And where does it go? Well, it goes to the skin, right? And that's how you get burned. In this particular example, from 1 gram of water, of liquid water at 100 degrees Celsius. Right? So we use a specific heat of liquid water in this case. If you can look at it in your table. So the second part of this says now to determine the amount of heat deposited by 1 gram of steam. So now we have 1.00 gram of steam at 100 degrees C. So not only are we going to have change in or transfer heat from the temperature change, but also we're having now release of heat due to a phase change. So now we're going to go from steam to liquid H2O, still at 100 degrees Celsius. And then the temperature of the water is I'm going to go from 100 down to body temperature, just 37 degrees. So we have 2 steps to account for in this case. We have the phase change over here. And then we have the temperature change in the second step. Okay, so let's take a look at how we can calculate this. We have our 1 gram of water, and we can calculate the delta H. I'm sorry, we can calculate the heat of that process as the steam condenses as being equal to the delta H of vaporization, and then times the number of moles of the water, the H2O that we have, right? So we have 1 gram, we convert that to moles, so 1.00 grams of H2O. 1 mole of water is 18.02. So that will goes away. We end up with N here, a number of moles being equal to 0.0555 moles of H2O. Right, the delta H of vaporization we can look up from our tables, and that is negative 40.79. That's kilojoules per mole. Okay, so we substitute both of those values, and we get the heat released due to the phase change. So we have negative 40.79 kilojoules per mole times that by 0.0555. Moles go away, and we end up with this ends up being negative 2.26 kilojoules, and then we still have this is the heat released here due to the phase change. From the gas to the liquid, and then the liquid is going to have to cool from 100 degrees to 37 degrees. So again, that would be similar to the calculation we did previously. We have Q equals M times C times delta T. So we have our M there, 1.0 grams. Specific heat of liquid water now, 4.184 joules per gram degree Celsius. And then our freezing temperature again would be -63. Celsius go away, grams go away, we end up with the same value as we did previously. So that's negative 0.264 kilojoules. So this is due to the temperature change. Of the H2O falling from 100 to 37 degrees Celsius. So then the total heat release would be the sum of the heat due to the temperature change and the heat to the phase change. So we add those together. We have negative 2.26 kilojoules plus negative 0.64 kilojoules. And so we stick them together, we end up with negative 2.5 kilojoules. Right, so in this example, in part B, in our example here, if you were to see sort of where we are on our curve, right, we had in part A, so we can use a different color. In part A, we had liquid water at 100 degrees, cooling down to about 37 degrees. I think about this. So that corresponded to this amount of heat being released. In the second example, or part B, we're looking at starting off with steam at 100 degrees. So we're starting somewhere else on this curve and further down here, for instance. Right, in order to get again to that 37, let's say this is 37. In order to get to that point, we still need to go this way, right? So to convert now all of the vapor to the liquid state, and then the liquid cools down. So we have the sum of this phase change here in blue, right? So that's the amount of heat released, plus we're going to add it now to the amount of heat released as per liquid water cooling down. So this would be the sum here that we just calculated for part B of that problem. Which is a reason why if you get burned with water at 100 degrees Celsius, it's not as bad as if you get burned with steam at 100 degrees Celsius, because you have a lot of energy, a lot of heat energy being released when the vapor actually condenses to a liquid. That releases a bunch more energy than the actual liquid cooling down.